Okay, hey everyone. Today we're going to be going over a recent vulnerability that was found in the sudo command and how we can be exploiting that vulnerability to gain root privileges on a system that has a vulnerable version of sudo. So just a quick outline. I do want to give a little bit of background about this bug and about the situations where it's applicable, because there are certain flags that are used and there are certain use cases for sudo which might not be common knowledge. So I want to cover those real quick just so everyone's on the same page. And then we're going to dive into the code, and we're going to talk a little bit about how exploiting objects on the heap can differ a little bit from exploiting objects on the stack. And then finally I want to go over some quick takeaways and things that we can learn from this as security researchers going forward. So the first thing I wanted to talk about was actually this other command, sudoEdit. And the main difference between sudo and sudoEdit is that sudo, as many of you are familiar with, allows you to run a command as root, whereas sudoEdit, as the name would imply, allows you to edit a file. So in a situation where you need to run some privileged command, like if you're starting or stopping a systemd service, you would be using sudo. However, you can use sudoEdit if you need to modify some configuration file or something like that that would require root privileges, but you don't necessarily want to run a sudo vim or something like that. And under the hood, the way that this works is the sudo binary has several different modes that it sets. So sudo can set that mode run, which allows you to run a program, whereas sudoEdit allows you to edit a program. Interestingly, though, things kind of get a little bit messy with the sudo-e flag, because that flag will enable that edit mode and also turn off that run mode. So when you do that, it's effectively similar, or it's effectively the same as sudoEdit. The other thing that I wanted to talk about a little bit was the shell mode in sudo. So we talked about that -e flag. There's also a bunch of different flags that you can enable, like the -s or -i flag, and those will effectively launch a new shell, or they'll run these commands in a new shell. And so that's really useful in situations where we have a series of commands we want to execute as root. So as you can see up here, we have a single command. We just want to echo that home, and that's going to echo as a user. It's going to essentially be executing in our current shell with all of our current environment variables set. So it's going to print out /home/Ryland, because that's my home directory for my user Ryland. However, if we execute that sudo-s, that allows us to spawn another shell, and then that new shell is going to have a completely different set of environments. You can even have a different shell variable set. So when we do that same exact command, that's going to print out /root, because that's going to be the default home directory for the root user. And when we enable that -s flag, because we have a completely new environment, we're going to be looking at the home for this user instead of for the Ryland user we were looking at before. And the way that it does that, just like how sudoEdit set that mode edit, and just a regular sudo command set that mode run, as you may have guessed, when we use that -s or -i and we launch a new shell, it sets a mode shell variable under the hood. And then many of you may be familiar with this, but it's a special edge case that I wanted to be talking about anyways, for those of you that may not be. And that's the idea of a special character. So when you look at an ASCII table, you have all sorts of printable characters. So like any character on your keyboard, that's going to be in the ASCII table. But you also have a bunch of other characters which are not printable. So in here we have all sorts of like end of transmission bytes and things like that. But the ones that we're going to be interested in for the sake of this talk and this vulnerability are these ones that are escaped by that \. So when we have a null byte, or like a new line, carriage return, stuff like that, those are all traditionally represented by a \, and then by some ASCII character. And so that's going to allow us to effectively encode this information into a string while still being able to type that out with our keyboard in an easy manner. So that's all the background information that I wanted to go over. And now we can kind of jump into some of the more interesting code. So we'll be jumping into the particular code here that's caused this vulnerability. So for this first section of code, I wanted to highlight a couple of pieces here. The first is we're checking these different flags. So if you remember before, we were talking about a mode run when you're just using sudo without that -e flag. And then we also have that mode shell, which is enabled when you use that -i or -s flag. And so what this section of code is doing is basically checking to see, are you running sudo with that -s or that -i? And if you are, it knows that you're trying to launch some sort of interactive shell, or some sort of new shell, I guess I should say, and execute those commands as root. However, when you do this, it executes a little bit more code. So in this little curly bracket, I've highlighted some code here that's basically going through every string in argv and then going through byte by byte and checking to see if it's any kind of special character. So we can see this, this comment here says that it's looking for potential meta characters. And if it sees any potential meta characters that don't match any of these characters in our whitelist, then it's just going to escape those, and it's going to increment and move on. So this code here is essentially filtering out any special characters that we might be able to abuse. So we really don't want this code to be executed. We really want to make sure that when we're crafting our exploit, we find a way to have that that -s flag or that run mode set, but not both of them. We don't want to have both of those set, or else our command line arguments will be filtered. And that kind of brings us to this next section of code here, and I've highlighted a couple more pieces. So as you can see, we have a few more conditionals, just checking to see, are we running, editing, or checking? We haven't talked about that check mode. That shouldn't be too important for the purposes of this talk, though. So effectively, this section of the code is calculating the length of a buffer, and the way that it does that is you have this 2D array for argv. You have an array of character arrays, because that's how strings are represented in C. And so for each string in that that argv, we go through, we find the length of it with strlen, we add 1 because we know there's a null byte, and we append that onto a running tally of the total size. And then we allocate on the heap some buffer user args of that size that we calculated. So that's going to be looking at every single byte in our command line arguments and accounting for it. In this next section of code, things start to get a little bit more interesting. We can see this is specifically looking to see if we're using that mode shell that we looked at or that we were looking at before, that we were able to trigger with that -s or even that -i flag. And if that that flag is set, then we're going to go through and we're basically going to make a copy of those command line arguments. But because argv is kind of hard to work with as a 2D array, what this is going to be doing is this is just copying it into a flat buffer. So it'll take just that that user args buffer that we allocated before, and it's just going to throw everything into a singular buffer to make things easier to work with. The way that it does that is, as you may have guessed, fairly similar to what we were doing before, where we loop through and we copy from that that old argv into this user args that we've allocated. However, where things get a little bit more interesting is on this line, 866. And in this line, we're looking to see if any of these characters is a backslash, because we know that if it is, it's escaping the next character. And so we check to see if that backslash is escaping some character other than a space. And if it is, we know that whatever that character is, it's going to be special. It's going to be some sort of command character, some sort of command byte that's going to indicate a new line or a tab or something of that nature. And so we're just going to jump right over that. And so this is perhaps a somewhat subtle bug, but it's a really powerful bug, because we're skipping any character, any byte that follows that backslash. And so some of you may remember that in C, strings are terminated with a null byte. So we can basically just take our command line arguments here, we can take our argv, and we can pass in some string that ends with a backslash. And when we do that, it's going to read through, it's going to jump over that null byte, and then it's just going to keep on reading. However, when we were calculating the length of that buffer, we didn't take that into account. We didn't skip over any bytes. So this is effectively going to be allowing us to write past the ends of that buffer, because we have a fixed length of every byte in that string, and then we can pass in a backslash as the last character in our argument. And we will continue reading whatever happens to be in memory after that null byte. And so this is a really powerful bug, because it turns out this is very easy to control the data which is on the stack after that null byte. The way that the stack is set up, your environment variables, your env there, is actually allocated right above that command line argument, that argv. And so I just threw together like a quick C program here to demonstrate that concept. We have argc, that's the argument count. We have argv, which is the vector of arguments, and we have that env, that pointer to a list of environment variables. And so we can control that environment that's passed into our program. We can control those bytes that occur right after the null byte in our command line argument. And so we can see when we run this program with no command line arguments, with no special environment, it's going to pass, or it's going to print out the number of arguments is 1. That's just going to be the name of this program. And then it's going to print out that first environment variable. In this case, that's just going to be something that's default. That's going to be irrelevant to us. However, we can set that very easily with something like the env command. And so here, we just pass in env-i and then some arbitrary string. And then we execute that code. And when we do that, we can see here that the environment variable has actually changed, and now the bytes on the stack after that argv are going to be completely different and completely controlled by us as the user. So just to recap, at this point, we can control the size of the buffer that we allocate. So that's going to be important for reasons that we can talk about a little bit later. And then also, we can end our arguments with a backslash. That's going to allow us to keep writing into this buffer of a fixed size that we can control. And we can even control those bytes from the environment variables into that fixed buffer on the heap. So we do still have a bit of an issue, though, because if we remember looking at this code, we want to make sure that we have that mode shell enabled, we have that edit enabled, but we know that we cannot have that run enabled if we have that shell enabled. So we need to find some way, if we want to reach that vulnerable code path without triggering the condition that will filter our input, we need to find some way that we can have mode edit and mode shell turned on, but not mode run. And so just to recap, we know that if we run sudo without any flags, we have mode run turned on, but no other modes. If we have sudo-s, then we're going to have mode run turned on, but we're also going to have mode shell turned on. If we run sudo-e, we're going to have that mode edit turned on, but because we have that mode run turned on, that combination means that we'll be triggering that filtering code. And then, of course, we can also run sudo-edit, and that's going to turn on that mode edit, but it won't necessarily turn on that mode shell that we also need. So this kind of gets us into an interesting situation where we know where there's a bug, but we don't necessarily know how we're going to trigger it yet. And so we have to get a little bit creative here, and we have to figure out a way to get to that vulnerable code path. And as it turns out, that's actually really easy because of the way that sudo and sudo-edit are written. It turns out that sudo-edit is actually just an alias of sudo. And so to make things a little bit cleaner, they've kind of compiled both of these programs into a singular binary because they're performing very similar tasks. And so the way that they check which mode it happens to be operating in is they just look at the name. They look at that first argument to argv, essentially, and they look to see what the last four letters are. If it's edit, they know that you must be running this as sudo edit instead of just a regular sudo command. And when you do that, this will automatically turn on that mode edit. So when we know that, things become a lot easier because we can take that sudo edit, and now we have the ability to recycle those same flags we were looking at before. So we know that we can pass in that -s to turn on that mode shell, and when we're running sudo-edit doesn't turn on that mode run. So that's going to get us into the perfect situation where we have mode edit and mode shell turned on, but not mode run. And so that's going to be the trick to how we actually trigger this bug. So now that we know how to get to the bug, we actually run into another interesting situation. We haven't really talked a lot about the heap before, but last semester we talked pretty extensively about exploiting stack-based buffer overflows. On the stack, we have a lot of really interesting function metadata. And so the one that we were really looking at a lot before was return addresses. So if we have a stack frame that looks like this, we have some local variables in your function, we have a stored base pointer, and then above that we have a return address. So if you have some variable here, you're going to be overflowing up into that return address. However, once we're looking at the heap, we don't really have that kind of luck. We don't really have that kind of opportunity presented to us. We have our user data stored here, and when we overflow, we're going to be overflowing down, because if we remember, the stack grows one way and the heap grows the other. So when we overflow into these pointers, these forward and backward pointers, not any interesting return addresses. Now, what these forward and backward pointers do is actually really interesting. The way that the heap, at least in glibc, is implemented, I'm sure that there are other implementations that differ a little tiny bit. But the way that it's implemented in glibc is actually as a doubly linked list. So you have a little bit of metadata specifying the size of this chunk, so how big this user data is effectively, along with the one before it, and that becomes really interesting when we start to free chunks. And then we also have these forward and backward pointers so that we can navigate between different chunks, and those also become really powerful once we start allocating and freeing chunks. Unfortunately, because that's such a complex topic, we'll probably have to dive into some of the details of that later on, I don't think that we'll be able to cram those into this this conversation of this bug in sudo, unfortunately. And that's really lucky for us because the way that a lot of these proof of concepts are written, they're actually not targeting these pieces of heap metadata, but they're actually targeting these special structs. And sometimes we get lucky and these special structs actually have function pointers, and so we can just overwrite a function pointer, and it behaves exactly the same way as if we had overwritten a return address. But in our case, we're actually overwriting some other sensitive data, which will allow us to gain code execution later on. When we exploit this heap metadata, when we overwrite those pointers, there are some really interesting ways that we can turn those into write primitives, and we can do some really powerful things with that. But luckily for us, we won't have to dive into that so much for this vulnerability. So I mentioned that we would be targeting a special struct, and specifically that struct that we'll be targeting is this service user struct. And this service user struct is used in a function called NSS load library, which is called in libc. Basically, as the name would imply, it's used to load libraries. And the argument that it's passed in, that service user struct, is usually heap allocated. So we know we have this this heap-based buffer overflow. We know that we can corrupt data on the heap, and we even know that because we control the size of that allocation we make, we can kind of control where that overflow starts. And so that's a topic that we'll talk about more in a later heap talk, hopefully. But basically, all we need to know is that we have this controlled overflow, and we want to find a way to get into this NSS load library so that we can overwrite some of these interesting fields in this struct. We can overwrite effectively the data that defines what library we're trying to load. And once we control that that library, we can actually load our own malicious code. So instead of loading, for example, some string parsing library you might want to use, we can load in some malicious library which will allow us to execute our own code and gain control of the system. So real quick, before we talk about those takeaways, I actually wanted to give you a quick demonstration of what this code looks like. Oh. If I can unlock this system, there we go. So right here, I'm actually using a publicly available proof of concept exploit. This can be found on GitHub, and we've actually included some resources at the end of the presentation. So if you're curious at about like how this exploit works, you should be able to track this down on your own, and you can read through all the source code and try it out yourself. But I specifically wanted to direct your attention to this section down here. You can see that we have these two buffers, this padding effectively, this smash A and smash B. We're going to allocate those of some length that we've predetermined. The way that this particular proof of concept works is actually really cool because it has hard-coded offsets. They've gone and they've calculated the offsets for different versions of Ubuntu and different versions of sudo. So whatever your system is, you should be able to just plug in that appropriate information and be good to go. So it allocates these buffers with these fixed lengths, and then as we had talked about, it's going to take that last byte and it's going to make that a backslash. So that's going to allow us to skip over that null byte at the end of the string and just keep on reading. And then that argv, as we would expect, we're running sudoEdit. Instead of sudo, we have that -s flag, that shell flag. So that's going to enable that mode shell. Then we have some padding. We have another series of backslashes here, so that's going to let us jump over another null byte and keep on reading into that buffer. And then down here, things get a little bit more interesting because we allocate that, that environment that we want to be passing in. And so we can see here, it's just a whole lot of backslashes until the end where we have this, this x/pop shells string. And so if we look at that libnss folder here, that directory, this actually contains a library that we've compiled for this system, that SO, that shared file, that shared library, called pop shells. And so what this is going to be doing is effectively we have a bunch of padding, we figure out the right offset that we need to get to write into that struct that we were talking about before, that struct that will define the library, and we just replace the library that we're loading with this custom malicious one. And so just to show it off in action real quick, we can do that sudo hacks me a sandwich. That's going to list all the different targets that it can support. I know right now I'm using Ubuntu 18.04, and I'm using this particular version of sudo with this particular libc. So we can just run that one more time with the corresponding argument. That's going to set those hard-coded offsets that we were looking at before. And when that happens, we can see I am now root. I now have all of the proper IDs, that user ID and group ID is 0. So I now have super user privileges on the system due to that very simple heap-based buffer overflow and being able to replace that shared library with our own custom malicious code. So now that that demo is out of the way, I want to jump back real quick and I want to take a look at some of those takeaways, some of those things that we can learn as security engineers from this vulnerability going forward. I think one of the biggest things that took a lot of people by surprise about this bug was that just because this piece of software was widely used, I mean, sudo is used everywhere. It's used on Linux, it's used on Mac OS, it's used on BSD distributions a lot of the time. It's everywhere. And it's open source, so people have been looking at this for many, many years now. However, this bug has been present in sudo for 10 years. And even with all of the eyes on this piece of software, nobody noticed it, or at least nobody noticed it publicly until today. And so when people talk about open source software being really secure because it has so much community backing, so many people looking for vulnerabilities, that's often the case, but not always. Sometimes things still slip through the cracks. And then the other thing, as developers, those special characters can definitely be a royal pain, and so we have to be really careful about how we handle those so that we don't end up in situations like this going forward. And then a couple more additional resources here. We have the original disclosure. So this is a really wonderful write-up of how this this code works. We lifted many of the sample code, much of the sample code that's taken directly from sudo, from this write-up. Because I think it does a really good job of focusing in on the relevant code and kind of filtering out the irrelevant stuff so that you can really understand exactly what's happening and exactly what's wrong. We didn't go as deep into the inner workings of how the heap works, but Azaria Labs has some really amazing resources on heap exploitation. So I highly recommend anyone who's interested in that check out her series of blog posts on the heap. We also have this proof of concept that I was using. This one is by Blasty, and this is by far the most stable one that I was able to find. This is a really cool implementation of this this exploit. And then we also have a little bit of a write-up on how this works, because there are a lot of different ways that this vulnerability could have been exploited. We see a lot of people using race conditions and things like this, and things like that. But this write-up was actually a really cool resource to understand how this particular attack worked, and how that NSS library load function can be hijacked to load our own malicious code in. So yeah, I hope everyone learned something. I hope everyone had a good time. And with that, I think we will be ending the talk for the day. We will see you all